Hi, my name is Leonard Facchinetti, and let's write some code together, shall we? What we have on the menu today comes in three parts. First, I'm going to show you some things that I developed since the last stream, and I developed them off stream, so I'm just going to cover them briefly. Second, we are going to look at all the different flavors of the Rbj filters, and I'm going to talk more about what they are. And then third thing is we are going to implement them in our JSFX library that we are developing together. It's this library that is going to help you develop better looking and easier to develop and easier to use JSFX, which are real-time audio processors for Reaper. So first of all, what did I do since the last stream? I changed all the definitions of the data structures that we have been developing to add initial values. So in case you don't know, this library that we're developing together comes with data structures. It will have some algorithms. Here is an example of a very simple algorithm. And it will come with a design system with like decisions on colors that you should use and spacing and font sizes and everything, so that it will be easier to develop the effects, hopefully, because these helper functions will help you out. And your effects will have a better user interface because you are going to be using a design system, which is always a good idea when you're designing a user interface. So in terms of data structures, they all have an initial value now. Before, that was last Friday, the initialization of memory was always with the undefined value, but now it is with this initial value that you have to pass explicitly when you want to allocate some memory. And that, of course, percolates throughout the data structures. The boxes already had a notion of initial value, but then we have structs, and unfortunately for structs, it doesn't really make sense to pass an initial value because when you are creating a struct, there is a variable number of positions in that struct. So I cannot really know how many values to receive, and there is no notion of functions with a variable number of arguments in JSFX. So for structs, I still initialize stuff with undefined. But for arrays, you have to pass an initial value, and then the whole array will be set to that initial value, which may be something like 0, for instance. It's a common initial value to have. And then a circular counter already had a notion of initial value, so nothing changed there. But for circular buffers, I added the notion of an initial value that is the value in the buffer to begin with. Most probably 0, but you have to be explicit about it when you are creating a circular buffer. And of course, because I changed all this in the library, I changed that in the example as well. So I have this effect that is for demonstration and for testing. And in this, I'm using the library. So I changed the tests and the demonstration accordingly. And Bo is here. Hey, Bo, great to have you. How is it going? Great. How are you? And where is Arya? I don't know. I think that he has to work at this time, and that's why we transferred the Tuesday streams to Monday. So I don't think we are seeing Arya today. All right, so that's what I did off stream. I added a notion of initial values to all the data structures. That makes sense. Not all of them, absolutely, just the ones that make sense. I guess it was like 2 or 3 of them. Now let's move on to the second item in the agenda, which is to look at all the definitions of the Rbj filters. So quick intro. What is a filter? It is something that is going to separate the signal in 2 parts. Typically, in audio, we want to separate like the low frequencies from the high frequencies, or we want to separate a range of frequencies, or we want to eliminate a range of frequencies. So a filter is just that. When you see an equalizer, it's a series of filters put together. And we do filter. I have another stream with Arya, probably our first stream about JSFX, in which I went into a lot of detail. What is a filter? How to design filters for audio processing, the typical design that you see with infinite impulse responses and whatnot. But now that I'm just going to take most of that for granted. If you're interested in more of the mathematics behind things and the logic behind things, you can go watch that stream. And in fact, we have implemented the Rbj filters in that stream. I guess it was a second stream on that series. Rbj just stands for Robert Bristol Johnson, who is the author of these equations that we are going to use. And this document, I guess it was initially written in 2001 and it has been floating around the web forever. And people keep creating new versions of the document in all these different places. So what I did is I collected all the different places and we are going to try to see if they have any difference. If anything was like an issue with the original formulas that have been fixed later. So I think that we are going to start with probably this email is the original definition of these filters. I suppose they are. After my quick research, I think this is the original post. But we are also going to consult some of the other ones. And I meant to like really go in depth and try to see the differences between them before the stream, but I didn't. So here we are. And Bo says, just checked your repack video. Gonna need to watch it again. Okay, sorry. Probably I didn't make a good job of explaining things, probably. But yeah, Bo, for those who don't know, Bo is developing compressors and also filters, but using a different technique than the one we are going to use today. And now I told Bo that he needs to publish this to Repack so that everyone can use it. And that's what he's talking about. So yeah, Rbj, Robert Bristol Johnson, has defined these equations for filtering, and we are going to implement them in our library. And briefly, I'm going to go over what these filters are, what they're good for, what they're bad for. So they are different flavors of filters. We have a low-pass filter, a high-pass filter, a band-pass filter, two different flavors of that, and a notch filter, and an all-pass filter, a peaking EQ, which is like just a bump in the EQ curve, low shelf, high shelf. Very straightforward stuff. And the equations are super simple to use, and they are super, super fast. When you are using these filters, it processes like it's a no-brainer. Can have like dozens of these filters on the signal chain, and your computer will not care about it. And in this document, it's from 2001. The person is even talking about things like implementing this on very old hardware to today's standards, of course. So if this kind of hardware can deal with these filters, then our computers are going to handle this no problem. But why are there other filters? Why don't people just use this one? Well, first of all, it is a filter that is designed for audio processing. It is going to have a relatively good frequency response, in the sense that if you want to separate a low frequency from a high frequency, maybe you want to get rid of the low frequencies because they're just rumble, and you want to keep the high frequencies, so you would use a high-pass filter for that. Well, these filters have a good separation of the frequencies, so that's a good thing. But in terms of artifacts in the time domain, the waveform, these filters are not good. They are designed to have a good frequency response, not a good time domain response. So there is no be-all and all of filters. Every filter has a trade-off. And that's the trade-off that we have in this situation. Good in the frequency response, bad in the time domain. But that's not all. It is also not good for automating parameters. So if you expect to do a filter sweep, these filters will work, but they may not be the best. They are not super, what people would say, numerically stable. So if you have the filter just sweeping around the frequency spectrum, you may have some artifacts from that. I don't think that you would notice this. I haven't really tested, but people say that you should not be using these filters, for instance, for a synth, where you probably have an LFO automating the filter frequency cutoff. So there are other equations that you can use, and in fact, I am planning on implementing some of these other equations that you can use in these other contexts. And of course, there is the ubiquitous issue with digital filters in general that tend to cramp at Nyquist. So the frequency response goes from 0 to half of your sampling rate. So if you're sampling at, for instance, in my Reaper installation here, I'm sampling at 48 kilohertz, and that means that I can represent frequencies in my digital signal from 0 hertz up to 24 kilohertz, which is half the sampling frequency. And when the filter, it has a nice round shape. When it gets closer to that 24 kilohertz frequency, it starts to cramp, goes out of shape. And these filters will not help you in that regard. They are going to cramp at Nyquist, which is usually not a big deal. So these filters can be useful for many kinds of tasks. I just wanted to highlight some of the pros and cons. All right, so GSPT4760, hey, what's up? Great to have you here. And so Bo is saying no tilt EQ. Yeah, probably we are going to get to those kinds of more esoteric filters in the future, but not today. Today we're going to implement the easy stuff that is good for many things and that many people are just going to use these filters and not think about it. For instance, if you are just literally implementing an EQ and it's a simple EQ, maybe the 2 or 3 knobs for like the cutoff frequency of a low pass and high pass filter, that sort of thing. You can get away with Rbj filters for that just fine. And I think that it is similar, if not exactly the same as the filter that comes with Reaper, the REAQ, not to be confused with REAQ, it's REAQ. So this filter, as far as I understand, it nulls with the Rbj filters. So this filter in spirit is exactly the same as the Rbj filters. All right, so GSPT4760 says, hi Leandro, just letting you know that your stream is breath of fresh air after my first day in university. Okay, sorry to hear that your first day wasn't great. What is that you are doing in university? Are you a student? Are you an educator? And what are you studying or teaching? What are you up to? Okay, so while you write your answer, let's start the implementation of this filter. So the first thing we have is this equation right here, which is the most straightforward implementation. So let's make sense of what is in this formula. And that's something that, again, if you want more detail and you want things at a slower pace, then you can watch our previous streams. But basically what this is saying is, Y is your output, and N is an index. So if you had something that is like, you have recorded some audio and you want to run a filter on that audio and produce some output, then in that case, it would make sense to think of N as the index of a particular sample in that audio recording. But that's not what we are doing. What we are doing is a real-time audio effects processor. So in JSFX, we don't have access to, we don't have access to an array of samples or to a list of samples or just a block of samples. We don't have access to that. What we have access to is the current sample. That's it. We have access to the current sample. The sample that we are currently looking at, that's the sample that we have. So this N index, we'll have to think more about how we are going to implement that. And X is your input. So this is the sample coming into the effect. This is the sample coming out of the effect. And N is the current sample. N minus 1 is 1 sample ago. N minus 2 is 2 samples ago. So we'll have to get a hold of previous samples. But I just said that in JSFX, we only have the current sample. We only have access to xn, effectively. We don't have xn minus 1 or xn minus 2. So to work around this, what we're going to do is our effect is going to use one of the data structures we defined, the circular buffer, and it's going to keep track of the 3 most recent samples in the circular buffer. So when a sample comes in, we process that using this formula, but we remember the sample because on the next time we run around the loop and we are starting to process the next sample, then we have stored the previous sample to use. And of course, when it's 2 samples from now, then the current sample will be the sample that happened 2 samples ago. So we are just going to use a circular buffer to keep these guys around. And we are also going to use another circular buffer to keep these guys around because yn is our current output. And we also have to remember the output from 1 sample ago. And we have to remember the output from 2 samples ago. So that's what it's about in this formula. So this is the heart of the filter, this equation. So if you want to separate frequencies, notch some frequency out of your signal or bump some frequency to emphasize it, all those kinds of filters boil down to this formula. It's awesome. It is so powerful. It's such a simple formula, and yet it can do so much. So this is the heart of the formula. And then what is these B's and A's? What are they about? Well, these are the so-called coefficients. So before we just add up the current sample with the previous sample and 2 samples ago and subtract the previous result and subtract the result from 2 samples ago. Before we do that, we multiply each of these guys by a coefficient. And the coefficient is going to determine what the filter is going to do. Depending on the coefficient that you have, the filter is going to act as a high pass if you use this set of formulas for these coefficients. But if you use a different set of formulas for the coefficients, then it's a high-pass filter, or a band-pass filter, or a notch filter. So we are always going to apply the exact same formula, but we are going to use different coefficients and have different results. So I guess let's start sketching some code here. But before we do, I'm going to catch up with what you all are saying. Physics student spent 1.5 hours learning why 1 is not equal to 0. Lol. Oh yeah, that is not an easy thing. I remember that lecture. I probably had it like in calculus. And people back in the, I guess, early 20th century were writing literal series of books to try to prove that 1 is not equal to 0 using set theory and whatnot. Hilbert, I think, is part of this endeavor, the mathematician. And it's not an easy thing. And yet it's kind of important that 1 is not equal to 0. It was not bad, but it was a long day. Yeah, Zoom classes are not good. Yeah, that's a whole conversation we could have because I was not in that environment. When the pandemic happened, I was already out of my PhD, so I did not teach online. But in one sense, I can understand why Zoom classes are not good. But in another one, I kind of prefer it that way. I mean, that's one of the reasons I decided to not teach in academia and instead do YouTube. I just think it makes more sense because you can connect to people who have similar interests instead of just connecting to students who happen to want a diploma in that area, so they have to take your classes. It's a whole conversation that we can have, but I think there are good sides. There are good sides to classes happening in Zoom. I don't know. I don't know because I haven't experienced it really. I was out of the education system before it happened. Okay, so what's A0, A1, A2, B0, B1, B2? Okay, I hope that I have answered this already, but these are the coefficients. They are numbers that we're going to multiply the samples as they come in, and also the previous results that we have accumulated. Though we are going to multiply using these coefficients, and they are going to determine what the filter does. The coefficients are going to determine whether this is a low pass or a high pass filter, for instance. And what does X do? X is just the sample that comes in. So In this case, it's the current sample or one sample ago. What we in JSFX call SPL0, for instance. That's what X is. All right, but keep in mind that I am, of course, explaining all this thinking that you want to implement an EQ and that your samples are coming in and there are samples coming out, but in fact, this is a filter to filter a signal, not necessarily a sample or a bunch of samples. What I mean by this is that sometimes it is useful to think of other things as signals that you can process. For instance, suppose that you are doing a compressor, and to do a compressor, the samples come in and you calculate some measurement of gain. Maybe it's the peak gain, maybe it is the RMS, maybe it's LUFS. You calculate some notion of loudness or of power, of gain, volume, however you want to think about it. But you calculate that. And that curve is going to be shaky, right? Even if you do something like RMS, which is going to smooth out the curve a little bit, it's still going to be lots of ups and downs in that curve. As the signal comes in, some parts of the signal are louder and some parts are quieter, and that is going to change like in milliseconds. And you don't want your your compressor reaction to be as fast as that change. So what you can do is use a low pass filter in that signal. So you calculate the volume, the gain, the RMS, whatever, and you use a low pass filter to smooth out that signal, and that is going to be the gain reduction that you apply to the signal in the end. As a compressor, that's what you do. You want to calculate the gain reduction to apply to the signal. Now, of course, there are different kinds of filters, and this filter here I don't think would be ideal for that task. As I explained before, this is a filter tailored for the frequency response, not for the time domain response. But there are other low-pass filters that are good for the time domain response. And you can reason about what you're doing in the compressor in terms of filtering signals like this. So for the rest of the day, I'm going to talk about samples coming in, samples going out, audio signals in general. But keep in mind that filters can be useful for other tasks as well. Okay, GSPT says the problem with Zoom classes is that having a full day of classes in front of a computer, seeing a okay, yeah, I can imagine. But I mean, it also gets old to watch a dude on a whiteboard, and yeah, I understand. And a lot of them don't know how to work with Zoom computers. That's bad. Yeah. And I understand, because it is a lot of effort to put something that looks like this. And I'm not saying that this is perfect, but it is better than most people. And it was a lot of work to put together. I mean, I had to test different lights, different cameras, different backgrounds, different settings in OBS, and it's still not perfect. So yeah, I understand why it takes a lot of effort to get something that is passable in terms of quality. And oh, let me tell you, an educator does not have time for that. Okay, so wasn't n sample 1 divided by sample 0? Oh, no. So this n is how many samples ago. So this is in terms of time, okay? So if you think about some audio on the Reaper timeline, this is going left and right. This is time. And sample 1 or sample 0, these are different channels. So at a given moment, there will be multiple channels in your signal, if your signal is stereo or quadraphonic or whatever. So 0 and 1 in this context, in the sample context, that means the different channels, while the n means channels from some samples ago. So you're thinking about time here, and you're thinking about space here. Yeah, a low pass for compressor pilot signals. That's my game. Yes, that's why I brought it up. And Bobs is here. Hey, Bobs. Hi. So some trigonometry is creating the curve within the filter. Yes. There is a bit of history, and I guess I can go into that, about how these equations come about, because if you just look at them, I mean, how does one figure these things out? And they kind of, Robert kind of explains this thing here, but for the non-initiated, it doesn't really make sense. Like, for instance, when he talks about BLT, Bilinear Transform, what is that about? Well, you start from analog filters. Why do you start from analog filters? Several reasons. First, there is a lot of history in analog filters. People have been studying filtering using analog circuits for a lot longer than we have been doing digital signal processing in the computer. So there is a lot of material, there is a lot of knowledge around analog filters, and they work fairly well. And second reason why you would want to look at analog filters is that they have some nice properties. For instance, they don't cramp at Nyquist. Like I said, using digital sampling, using digital signals, you can only represent frequencies up to half of your sampling frequency, which in my case is 48 kilohertz. So I can only represent 24 kilohertz at most. And that has some implications in terms of what the filter looks like when you start approaching that frequency. And there are, of course, other implications in terms of aliasing and whatnot, but analog filters don't suffer from that because they don't have a Nyquist frequency limit. Now, there are other limitations in analog filters. It's not because it's analog that it's going to be perfect every time, and it's not like that. Analog filters have their own issues because of noise, and I mean like electrical noise on the line, and just because of heat and many other issues that are inherent to analog filters, but they do have some nice properties. So you start with an analog prototype, you start with an analog filter. Then you do this bilinear transform, which is just a mathematical operation to look at the circuit, to look at the schematic of a circuit. I think there is an example of this in the Wikipedia article for bilinear, not interpolation, but filters. Do I really need to look into this? Maybe it's here in this article. I don't know. No, this is not what I'm looking for. Oh, what am I saying? I'm not looking for bilinear. I'm looking for biquadratic. This is the kind of filter that we are going to implement, by the way, because if you look at one of these equations, you're going to find two squares. And that's why it's called biquad. But I forget where it is. Or maybe I'm even looking at the thing, I cannot find it. Yeah, I think it's this, right? This is squared and this is square, and that's why it's called a biquad. In any case, if you look at, for instance, this is the schematic of the filter that we are implementing today, actually. I mean, look at this. It's the same formula. So you start with this circuit, and you can just, I guess, believe that this is going to do what you expect it to do because this filter has been around forever. It has been used in analog stuff. So you look at this, and then the BLT, the bilinear transform, is a mathematical tool that you can use to look at this circuit and come up with equations to represent what this circuit is doing. And it's not exactly trivial because there are multipliers. Those are the triangles here. There are delays of one sample. These are these blocks. And then there is addition, but very importantly, it feeds back into itself. That's why these filters are called IIR, or infinite impulse responses. That's because there is a feedback loop. And that's the reason why this filter is not trivial to represent mathematically, because you have to think about how this feedback is going to affect the signal coming out. Okay, so you use this BLT thing, which is just a mathematical way of reasoning about this circuit. And you have to do a lot of work to make sure that this is going to pan out correctly. For instance, you have to take in account the frequency warping. I'm not 100% sure I understand everything that goes into this. I don't know how to do the bilinear transform myself. But when what comes out of this is these sets of equations. Essentially, that's how it goes. You start with an analog prototype, you start with an analog filter that has been around forever, and then you digitize that using bilinear transform. That's where these equations came from. Now, if you want to ask, where did this come from? How did people figure this out? I have no freaking idea. But maybe I'll learn, and if I do, then I'll teach you. Okay, so n is a stored variable. Sorry. Yeah, in essence, n is an index into a chunk of memory, and n is an index into a chunk of memory, and we have to store that information. So yes, it is a stored variable in that sense, but it's just an index into a place in memory for us. Okay, so let's start sketching some code here. Been talking for too long. And GSPT 4760 says that they can no longer stand just a dude in a 5 centimeter square babbling. So let's write some code. Let's first think about where I even want to implement this. It needs to come after the mathematical functions and the data structures, because I'm going to need some of these data structures. And I think that maybe I'll just put this after even the design system, maybe. No, I think I am not going to need anything from the design system in this. So I think I'm going to put it here. I'll put it like Rbj filters. And then we have to think about all this stuff that we have to keep around. So if we want to implement this formula, we need to keep around the old samples and our old results. So I'm going to have to define a data structure for this. And I'm going to start with a struct. So Rbj filter, and this is going to be private. This struct is going to be private. I will have functions that you can call to create this data structure. And this is just a struct define. And that's how I call this, right? Yes. Then this struct is going to have some fields. And that's how you define a field, right? Yes. What I'm doing here is I'm searching, and if I see more than one occurrence, then it means I got the name right, because the name has occurred elsewhere in the file. So I guess one of the important things is, let's say, the previous samples. So I'll have maybe an X. So let's make our code resemble this document as much as possible. So I'll call this the axis. And then also some Ys for these locations. And we will need to store the coefficients. So the coefficients are going to influence what the filter is, if it is a low pass or a high pass, but the coefficient is always also going to determine like the cutoff frequency and if there is some resonance. All of those parameters of the filter are going to be determined by these coefficients. And usually people don't do this division every time. They just calculate B0, B1, B2, A1, A0, A2. I said this in the wrong order, but you got what I mean. You just calculate the coefficients and then you do this division. And this is so-called normalizing. So what we are doing is we are normalizing the coefficients, so we don't need to store A0. We are going to normalize stuff so that we don't need to store that. So we only need to store B0, B1, B2, A1, A2. So those are the coefficients we need to store. So maybe I would just have something like A and B. And I am also going to store, I don't think it's strictly necessary, but I think it's a good measure for me to store more things like The sampling rate I'm not going to store, because if you change your sampling rate, then the plugin is just going to restart and everything is going to be different. So I'm not going to store the sampling rate, but I am going to store the frequency. And I suppose that even though you're not really supposed to be automating this parameter because it will not hold as well as some other filters that we may implement in the future, but still I wanted to be able to change the frequency. So I'm going to store the frequency. I'm also going to store the dB gain. And this is only useful for two kinds of filters, peaking and shelving, but if that is my kind of filter, so I guess that's another thing I need to store. What is my type of filter? And maybe I will have an enumeration for this. So let's have a to-do for enumeration for filter types. We'll get to this shortly. So we are storing the frequency, we are storing the type, and that means that we can store the dB gain, and I'm going to call this like dB gain. And in here it's using camel case, but we learned that JSFX are case insensitive, so if you spell this with a lowercase b, it's also going to be the same variable, so I decided to avoid confusion, everything is going to be lowercase. That's why I'm putting an underscore there. Then we have an option of how we want to represent how wide the filter is. So maybe if it's a filter that is going to bump some frequency, maybe I should show that with a graphic instead of my hands. So if I have my favorite EQ, which is not that guy, it's that guy. So if I have something like this, then how wide is this? And there are different ways of representing this. One is the Q, but it can the same idea can also be represented with bandwidth or with S when it's a specific type of EQ, a shelving EQ. So I guess I'm going to have an enumeration for this. Yeah, I'm going to have an enumeration for this. What is the type of wideness that I'm using? And I'm not really sure that wideness is the correct word to use in this context, but I'll deal. So I'll need an enumeration for widenesses types. And I'm also going to need, these intermediate variables are only used for computing the A's and B's, but it is so easy to just store them that I'm going to store them as values as well in the data structure. I'm not really going to use them. I'm going to use the A's and the B's, but I'll have them there just because I will. So we'll have an A, and that's a problem because capital A and lowercase a mean different things. So I guess that this one is more important. That is going to be our A's, and this is less important. So let's have a different name for this. What is this doing? This is like the square root of the dB gain converted to gain. So dB gain is measured in dBs. This is measured, this is amplitude, and then it's the square root of that. And we already have alpha as well, so that's not gonna fly. Maybe I'll call this like big A. It's not a good variable name. We may want to rethink this, but then we also have omega, and then sin and cos for sine and cosine, and then alpha and beta. Let's catch up with chat. We'll look up, thanks. Not really sure what you will look up. But okay. So let's check the order of this. Do we like the way that this is defined? I don't really like the way that this is defined. I think I'd rather have it like this. These are like the setup for the filter. These are the operation of the filter. So this is something that we can do only once. We can tell that this is the frequency, type, and so forth. And it's going to calculate all the A's and B's. So even that part is about the setup. So all of these variables are necessary so that we can compute these two variables. And then finally, these are the variables that are like the operation of the filter. So that's why I have this in this order, but we still need the enumerations over here. So let's define them. I will define Rbj filter type, and we will need all these types over here. So let's see. Low pass, and you can see that I'm spelling things out. That's a matter of preference of mine, and it's also like a political statement. I want to spell things out, make things more explicit. Not always. I have dB instead of the cval. But still, I want to spell things out when it makes sense to do that. And I think that in this case it does. So band pass, constant skirt gain. So band pass, constant skirt, and band pass, constant peak. Then we have notch. All pass, peaking EQ, and low and high shelves. Oops, low shelf, high shelf, and it's not all peaking, it's just peaking. So there you go, those are the types of filters that we can have. And let's also have an enumeration for the types of wideness. So Rbj filter. Oh, and I think it's super important that we put some references to where this all is coming from, right? So let me copy here all the references that I have. I'm probably going to look at all of them, maybe not today, but I will cross-check to make sure that, as I said before, nothing was like wrong in the first definition and then fixed later. Okay, is there a syntax highlighter for EL2 in VS Code? Not that I am aware of. I tried to find one and I couldn't find it, but I don't really care. I don't find that syntax highlighting helps me that much. Also, I can always use the editor in Reaper, which does have syntax highlighting. It even has auto-completion to some extent. But I don't think that just coloring numbers in green helps me write better code. Not in this context anyway. I think that there are other tools that are more useful. Things like auto-formatters is something that I use all the freaking time in JavaScript, and it just doesn't exist in EL2. Linters. Yeah, that kind of tool is the tools that I'm looking for, but syntax highlighter, not that important. That said, I think I am going to write a syntax highlighter for EL2 at some point in the future, maybe. It could be a fun project. Yeah, okay. We'll look at biquad out of curiosity. If I spark the curiosity in you, then my job is complete. That makes me happy. Benjamin, hey Benjamin, it's great to have you here. You are important. I like you. Leandro, just developed my first rescripts this past weekend. Thanks for your helpful videos. That makes me so happy. You are the best. Okay, what does the double underscore mean? Several things, actually. In the beginning, the double underscore means this is private. And that's something that I'm probably going to document when I start writing documentation for this. So in the beginning, double underscore means this is private. You should not be touching this. Oh, but in that, I guess in this case, you should be touching this, right? Because you're probably going to have to say which kind of parameter that you are passing into the library. But in this case, I don't want you touching this data structure by hand. I want you to be using functions that we are about to write below. So that's why the double underscore here. The double underscore here means just separation, because Rbj filter is a concept. this is a concept and this is a concept. Double underscore is just separating the concepts in that way. So that's why, for instance, I have bandpass and then double underscore. So it gives you a pause. And if you like squint and you don't see the underscores, you can sort of read this as you would in English. Not quite, but there you go. Yeah, so maybe you do have a project, GSPT 4760. Yeah, it could be fun to write a syntax highlighter for EL2. It could be even more fun to try to write an auto formatter so that I don't have to care about indentation and whatnot. And you can also do IntelliSense or auto-completion. I mean, it should be relatively straightforward because you can, first of all, just autocomplete by going to the JSFX webpage, and in there you are going to find, I have in my search history, JSFX. What is that about? Okay, it's an esoteric programming language, probably based on brainfuck. Whatever. You can come here and you will find all the functions that exist. So you can just write IntelliSense to autocomplete. For instance, if you go to the mathematical functions, you can just grab these names and maybe even the documentation. So it should be relatively straightforward to do an autocompletion. But I don't think that anyone has done that. So you do have a project. All right, so in terms of wideness types, see, wideness type is a concept, double underscore, then we have bandwidth, Q, and S. Oh, and did you see that? I just used autocomplete, but it's not autocomplete based on any smart thing. It's just based on the fact that this sentence, this word, has occurred elsewhere in the document. But you could be smart and just find all the mathematical functions in REAPER, all the memory-related functions in REAPER, and then you could also try to look at the functions that you have defined yourself, and that's relatively easy because all you gotta do is look at the file, look for function, look at the function definition, and if you have some sort of imports, it would be nice to traverse that and find the functions as well, which is something that JSFX in the REAPER editor is not capable of doing across files. You can autocomplete with a function that has been defined in the same file, but not across files. So that could be fun as well. Just traversing these imports should be relatively straightforward, and by relatively straightforward, I mean like it will take a while. It's not easy. It's just something that has been done, is doable, and there is probably good resources that you can find. Maybe, I don't know, haven't really checked. So you can do bandwidth, you can do Q, and you can do S. Remembering that S is only for shelving. Yeah. So we'll have to have a check. If you are shelving, then you can define the wideness using S. Otherwise, you are restricted to bandwidth or Q. And there is a nice formula somewhere in here to translate between the two. Maybe not on this version of the document. But there are formulas for you to use if you have Q or if you have bandwidth. I thought that there was also a formula to convert between Q and bandwidth. I know where to find this formula if it's not in this document. And it could be a nice auxiliary function. In the same way that I think that we should have this as an auxiliary function. This is converting from dB to amplitude. I have a video about this way back in the channel, in which I explain the relationship between dB and amplitude. All right, so we have the data structure definitions that I think we are gonna need. Let me just double check that everything that I wrote makes sense, and I think it does. So I'm going to commit what I have. And I was ambitious, thinking that maybe I could implement the whole thing today. Now I am not so certain anymore. Let's start writing one of the functions that we have to use to create one of these filters. So if you want to create one of these filters, let's think about the context in which you may want to create one of these filters. Well, I think it's gonna go somewhere in here. And let's say that I have a filter and I probably want to do, I will call this the Rbj filter, and I probably want to do something like Rbj filter new. But do I want to specify all these parameters, the frequency, the type, the dB gain, and so forth? Do I want to specify that here? I don't think so. Because it is common if like I have something like an EQ, a proper EQ. I just have an EQ effect that is going to use one of these filters. In that case, I probably want to have some sliders or graphical user interface. And that is going to determine these parameters, like the frequency. So I think that I'm not going to specify all these things in here. I'm going to leave this for a separate method. So I think that in this function, all we gotta do is allocate the memory the right way, right? Because in the init block, the block that we are right here, we need to allocate the memory that we are going to need. And we know that we'll need some circular buffers. We are gonna need maybe some boxes. So let's define this function to allocate the memory for us. So there is no way for this to go wrong. I don't have to do any kind of check. In most of my data structures, I have to check, like, if you have a size, it needs to be positive. That's that kind of thing. In this context, with the filter, I don't think I have to check for anything. I can just start defining the memory locations I'm going to need. So I'll call this the Rbj filter. And the last thing in my block of code is going to be to return this Rbj filter. And the Rbj filter is going to be lstruct new. So I'm going to create one of these data structures. This is the definition of the data structure. I'm declaring all the fields in the data structure. This is me creating one instance of. So I'm actually creating a data structure based on the recipe. Then I have to initialize all of these fields to something. That's what I'm going to do right now. So most of these are going to be undefined, I think. Let's think about this. Yeah, so I want to be able to change the frequency, the type, the dB gain, and so forth. So these are already locations in memory that I can manipulate, so I don't need boxes. In case you haven't been around, boxes are just one slot in memory, but this is a slot in memory, so I don't need a box here. And I think that I have a box somewhere else that doesn't make sense. Let's check this. Where am I using boxes? I think I'm using boxes over here on the test, and that's fine. But here in the library, I'm using box to store the struct definition. That makes sense. Oh, and those are the only two locations. So all right, I'm not misusing boxes. And then in most of these locations here, like the frequency, I don't know. The type, I don't know. The dB gain, I don't know. The wideness type, I don't know. So most of these are going to be undefined. But the A's and B's and X and Y's, those are not just undefined. They are data structures in and of themselves. They are going to be, I think that the A and B are going to be arrays. And I need to say what is the size of the array. So we said that the A's, we are only going to store A1 and A2 because we're going to normalize. We're going to divide by A0. So I only need two locations, but to begin with, they are undefined. Then for B, we're going to need three B's. B0, sorry, I'm in the wrong equation. I'll need B0, B1, and B2. So I need three locations and they're going to start undefined. Then for X's and Y's, they're going to be circular buffers. And I believe I have to say something like __ new for this to work, right? Yes. So I have to pass for the circular buffer the size and the initial value. That's easy. Same as an array. So the size of the X array is going to be, or circular buffer, will be three positions. We need to store the current, the previous, and the previous to previous. Or do we even need to store the current? I don't think so. Yeah, I don't think so, because I think that the way this is going to work is you're going to give me a sample and I'm going to give you the output. And then I'm going to store these guys for later. So I only need 2 positions. Oh, and you know what? I don't think it should start as undefined, because A's and B's and everything up to here depends on the configuration of the filter. What is the kind of filter? What is the cutoff frequency and whatnot? But these guys are just the samples coming in, and I think that I don't want to have to like fill in the buffer before I can start using the filter. So I'm just going to say that when you initialize the filter, the samples that are there are just silence. And the same for Y. And then I return this Rbj filter. So right now what we have is just a data structure with the right format. Then I'll need another function that I'll call Rbj Filter Configure. And as you imagine, this is the one that you would call, for instance, when a slider is changing, for instance. I don't know. And you will have to provide me with all of this information, all of these fields. The ones that make sense anyway, right? If you have something that is some wideness type. So where is my Q and bandwidth? What's that about? Oh, I think I forgot that. Let's have a field for that. So we'll have the type and the value. So this is going to be like Q, and this is going to be the Q, or this is going to be bandwidth, and this is going to be the actual bandwidth. So over here, you have to provide me all the parameters, and I will have to initialize all of these, and I'm gonna just store this for future reference in case you want to debug and you want to be able to see the frequency or whatever. But actually the goal of configure is to calculate the A's and B's. So we'll have to implement that function, and then over here, I guess in this case for testing, I would just call this configure further down below. Yeah, let's commit what we have. I'm going to check on chat, and then I'm going to continue. So over here on the demonstration, all I did was to just initialize the filter, and over there, I put in the new field, and I initialized everything. Now that I'm thinking about this, I think I will have 2 underscores here, right? Because wideness is a concept. And I think that is all. Yeah, all right. Yeah, let's see what chat is all about, and then I'm going to continue. I'm probably gonna do that some of that. Okay. Yeah, I encourage you to do that and let me know when you have something to show, because I want to test that. And Bobs says, is there a book you can recommend for beginners to learn the basics of scripting in Reaper? Does it rely on some standard coding principle? That's an excellent question. Okay, so there are different kinds of things you can do in Reaper. You can automate stuff, like the things that you would click around to do. You can automate that using Reaper scripts. And then there is the JSFX part of thing, which is for processing audio and video in real time. If you want to learn to script in Reaper, in the sense of Reaper scripts, you write those in 4 different programming languages, mostly in Lua. And you can learn how to write Lua. You can learn all about the language. I recommend the Programming in Lua book. It's not necessarily good for beginners in programming in general, but if you have some basic understanding of programming, then this is a great book to just cut to the chase and learn the basics of Lua, and you'll be good to go. But what's more important is to learn the APIs, the tools that you have to work with. The tools that Reaper is going to give you as the programmer on how to do stuff. And there is no book for that. There is no class for that. There is no video for that. Even the Reaper documentation itself kind of is lacking. So there's a lot of trial and error. And I think that at this point, in terms of videos, Arya and I are where it's at. There are some other videos, but they are like half an hour long and they just cover the very basics, or maybe 1 hour long. And we have been doing this consistently every week. So I think that watching our streams, and I explain as much as I can everything that I'm doing. So I think that that may be one of the best bets. Now, does it rely on other standard coding principles? The answer is kind of yes. As I said, even the Programming in Lua book kind of depends on learning how to program in general, which is a shame because Lua is an excellent first language for a beginner. And so is EEL2. It's such a small language with so few concepts that you can sort of learn it as a first language, but there is not a lot of material around that. And for JSFX, I don't know of anyone else on YouTube who has videos or is streaming about JSFX. I don't think it exists. And even the documentation, again, is not awesome. It is just a couple pages, and there is a lot that is like for the initiated. For instance, if I go to the JSFX page for like, let's say, FFTs, this is super concise. And what the hell is an FFT? Why do you use it? What is permutation in that context? What is real and imaginary input pairs? I mean, this is clearly for people who have been using FFTs for a while now. And yeah, there is no shortcut, unfortunately. So personally, what I am doing is I have a bit of experience in programming. I have been doing this for most of my awake time in this last 17 years. But what I'm doing is just reading some of the docs, reading a lot of what other people write. I'm learning so much from just going to the other effects, like this is a treasure trove of digital signal processing concepts and JSFX concepts. So I just read what other people send me, like Bo sent me this code, and I read what is in there in Reaper to begin with. I read stuff that I find in Repack, just read, and I start constructing ideas. And then I am reading this book that I find is a really good book. If you want to do, if that's what you mean by scripting, then yeah, if you will need to learn more about digital signal processing. So that's a good reference, and it is a book. Other than that, I have a project of maybe writing a book someday. So would you be up for that? Would you be interested? Like, my pitch for the book is, this book is excellent, but it is about a lot of things. It is about image processing, because image is also a digital signal. It is about sonars. It is about X-rays. It is about neural networks. It's about a lot of things. And you have to know your way around things to understand what is usable in the context of audio processing. So my pitch for a book is, I'm going to take you from nothing to being competent in digital signal processing for audio, for real-time processing, using JSFX, because that is such a nice language to use. So small, so easy to learn relatively. And it gives you like real-time feedback when you're programming. So I think it's a great language. That could be a fun book, or video series on YouTube or something. Yeah, I agree. The best way is to read JSFX plugins on GitHub, and that book is awesome. Yeah, but it's not ideal. As I said, I think there is a niche. I think there are 5 people who are interested in this book that I'm proposing. So maybe I will write it someday. It could be a fun experience. Okay. All right. So configuration of the filter. What do we need in terms of configuration? I guess it's mostly some of these, but not all of them. Yeah, we need some of these specifically, we need these guys. And I think I'm going to put a comma at the end of these and join these lines. And here I have my parameter list. Oh, I'm missing one. No, I'm not. But this order is weird, right? I think that the first thing I should say what is the type of my filter. Then another important thing is what is the frequency. And then even the dB gain is only for a couple kinds of filters, right? Yeah, dB gain is not super important, but bandwidth and Q is super important. So I will order this like type, frequency, wideness, and then dB gain. dB gain is going to be last. All right. All right, so that means that here I'll have type, frequency, wideness, and dB gain will be the last fellow. And that's how you configure the filter, by providing me with these arguments. From this, including that, I will calculate everything else. Alrighty, so first thing is I want to store all of these fellows in their right location. So, oh, I am not doing this the right way, am I? I shouldn't be assigning it this way. What I should be doing instead is I should be doing L struct set of Rbj filter on that field with that value. That's how you set something in structs using our library. What I had before was just redefining what it means. It was redefining this field index, which doesn't make any sense. So, all right, now I think I'm going to like copy some of these guys at least. I will copy these guys over for sure. And instead of L undefined, I will have essentially this. By the way, in case you don't know this, in Visual Studio Code, there is this really useful trick. If you hold Option, and I think it's Alt on a PC, then you can select more stuff. It's called multiple cursors, I think. So I can select all of these guys, and I now have 5 of them. And then I Command C. If I again do a selection of 5 items and I Command V, they go to the right locations just like this, which I think is a super nice thing. I really like this. So this is just me storing these values for later because for debugging reasons. But next we need to compute this guys. So let's go ahead and do that. So for the dB gain, for big A, we need to have that formula, which is this formula. Oh, and we need to check. So here I have a couple of things. I need to check if I am on a peaking or shelving EQ. So maybe let's do that. Before I even try to set up, because now there are error conditions. So I should check this. What is an error condition? My error condition is if my type is equal to peaking. So if my type is peaking, and my dB gain is set, right? dB gain is only for peaking and shelving. So if my type is not peaking and my type is not a high shelf and my type is not a low shelf my dB gain is not undefined, that's an error. Otherwise, we are going to calculate all this stuff. So what am I doing here? Well, I'm doing error checking. If you call this by mistake with a type that is incorrect with respect to dB gain, you're going to get an error. And if you want to use a type like a low pass that doesn't have dB gain, in that case, you need to pass undefined here. Yeah, let's double check that this logic makes sense. So if my type is not peaking, and my type is not high shelf, and my type is not low shelf, low and high shelf, so I guess I'm going to say low and high shelf here as well. There you go. So if my type is not peaking or low shelf or high shelf, these three types, and my dB gain is defined, it's different from undefined. There is a double negation, undefined and not. So if my dB gain is defined, it doesn't make sense. It doesn't belong there. So I'm just going to return an error. Otherwise, I'm going to proceed. Yeah, let's see how chat reacts to this. Okay, message redacted. That's the reaction. All right. So what is up? I'm computing big A, right? So I need to check. Am I in a peaking filter or low shelf or a high shelf? If so, I'm going to compute big A. Well, I think I'm going to do it like this. Right, so if my type is equal to yes, that's right. So if my type is peaking, or my type is low shelf, or my type is high shelf, then I'm going to use the formula. Or maybe I would just do it the other way around, like I had to begin with, for symmetry with this chunk of code here. So if my type is different from peaking and low shelf and high shelf, what is my big A? It is undefined. Otherwise, I need to use the little formula that we had, which is this formula. And at this point, I have an option. I can either define this with the most straightforward formula, or I can define it with this, which I think represents better what's going on. I think I'm going to use this version. In terms of computation, this is probably just going to happen once when you're moving a slider around, so it doesn't really matter if I do it this way. This one is faster, but I don't think it matters that much. So I think I'm going to use a square root of the dB gain, but I'm going to call a function that doesn't really exist yet, and we're going to have to define it. The intent of this formula, okay, there is a trade-off. What this formula here, the one I highlighted, what this formula is doing is it's converting a value in dB into a value in magnitude. So I have an option. I can either just have a copy and paste of this, and that's great, because it looks like the document that it's coming from. Or I can take the more educational approach of having an auxiliary function that goes like dB to amplitude, and maybe it will be in the library, so that kind of thing. And then I'm kind of teaching you, as you read this, I'm teaching you what this formula is about. And of course, I will not be able to do that throughout because I don't really understand everything that's going on here. But I can teach you that much. So, I don't know. It's a tough option. I can make it look like the document, or I can try to teach you something, which may be even misleading, right? You may not really understand what this is about. And you may be wondering, why did this guy do this change? Is it a fix? Is this a mistake in the formula that he's fixing? I don't know. At least I know something. I want to have like a dB to amplitude conversion. Yeah, and there is already notes here for me to remember that. So I think I'm going to stick with the document as much as possible. Yes, I'm just going to use this formula. All right, so yeah, I'm going to stick with the formula. So it's going to be 10 to the power of, what is it? dB gain divided by 40. Now put some spaces there. 10 to the power of dB gain divided by 40. Alrighty. And then for omega, it's that formula. And omega is not conditional. It always exists. So I can just copy and paste the formula over here. And then pi is represented in JSFX with a $sign like this. And then frequency is just the frequency variable. And then sample rate in JSFX is S rate. It's a variable that comes with REAPER and it represents the current sample rate. I can show you. It's going to be under the system variables and samples block. S rate, 48,000, 48 kilohertz. Then we have sin and cosine, and those are just the sine and cosine of omega. So maybe I will have a local variable called omega. Then for alpha, I need to check if I am in the Q mode or in the bandwidth mode. And what if I am in the S mode? I'm not even sure. Yeah, I don't even know. Maybe you don't use alpha in shelving filters? It's for shelving Q only, so let's look at the equation for shelving. Is it going to use... No, it does not use alpha. Let's look at the other equations real quick. So this is using alpha, that's using alpha, that's using alpha, using alpha, using alpha, using alpha, using alpha. So it's only in the shelves. So if you are in the shelves, don't calculate alpha. So it's going to be a similar story to the one we wrote above, where we check the filter type and then we do some computation. So if I have... I really have to think this through because all the negations are going to throw me off. So if my type of EQ is not a low shelf and it's not a high shelf, I am, for instance, in an all-pass filter and I do need to compute alpha. Guess I'm going to change this. No. I'm just going to stick to that. So if my type is not a low shelf and my type is not a high shelf, it means I am like on an all-pass filter, so I do need to compute alpha. Let's get the alpha equations. We have two of them. Otherwise, it will be undefined. So in here, I'm going to have another one of these conditionals. I'm going to check if my type is Q. So let's check the wideness type. And if it is Q, yes, Q comes first. So if my wideness type is Q, then I'm going to compute using this formula, which uses this thing above. So guys, I'll have some other local variables as well. And I only have like 10 minutes. I don't think I will be able to finish this today, you all. What do you think? If I can finish the configuration, I think I'm happy. So I'll have local variables that are omega, and I'm going to have another one that is omega sine, omega cosine. This thing that I'm doing now is called a extract variable refactoring. Very unsurprising, don't you think? Okay, I extracted this so that I could use them here. So that's the equation for Q. All I gotta do is use omega sin divided by 2 times, and this is not Q, this should be my wideness value. Otherwise, if my type is not Q but bandwidth, then I should use a different equation, which is this equation. And this is omega sin, and this is the hyperbolic sine function. So that does not come with REAPER, we'll have to implement that guy. And this is not bandwidth, this is my value. So it will be similar to this, the wideness value. And I forget what is the kind of logarithm that we have in JSFX. So let's check real quick. We want the natural logarithm. Let's go to the simple math functions and look at the log. Yeah, so the natural logarithm is just called log. So all of this makes sense, but we still need this mathematical function. So let's go and implement that real quick. Mathematical functions. Function sine hyperbolic of x probably. And let's go to the Wikipedia article for hyperbolic trigonometric functions. You can tell that I have been here before. And we have different ways of defining with exponential, differential, complex. No, I think I like the exponential definitions. And since we are here, why don't we just grab all of them? Right? So the hyperbolic sine of x is equal to any 3 of these formulas. They are all equivalent. So in all 3 of them, there is an exponential. There are 2 exponentials. So it doesn't really matter which one I use. I think that this one has the fewer operations, right? Just by eyeballing. So I think that's the one I'm going to grab. So this e to the power of is actually optimized in JSFX. It's called the exp function. So I can just use that exp of x minus exp of minus x divided by 2, but I do need parentheses around this to mean that I want the division to happen with the result of the subtraction. So that's my sine hyperbolic. Let's have a cosine, and let's also have a link to this page, which is where the formulas came from, right? It's a good place to have a link. And those are the definitions we are using. All right, for cosine of x, we are going to have something that is super similar, except that there is an addition here. Right, now let's do the hyperbolic tangent of x. There are different ways of defining this, but this is going to use more operations. So I think I'm going to go with this formula. Oh, but this formula has 4 exponentials, while this one only has 2. So I think I'm going to go with this formula. And this is exp of 2 times x minus 1 divided by exp of 2 times x plus 1. All right, and do we want these fellows? I don't see why not. So let's have a cotangent. And in this case, I think I'm going to go with this formula for the same reason as the tangent. So it's very similar, except that it's an addition on top and a subtraction at the bottom. I think I'm going to save this tab to read later. I want to learn where this stuff comes from. What the hell is a hyperbolic sine anyway? Okay. Cotangent, hyperbolic secant. I haven't seen that in a while. Hyperbolic. And then I have 3 options again. So this is going to use more operations. This one is straightforward. It has 2 exponents. This also has 2 of them. So I think I'm going to go with the one in the middle. My logic here is the fewer operations, the more numerically stable things will be in terms of rounding off errors and whatnot. So I think that everything will be better if I just stick to the fewer. And it may also be faster, which is a plus. And then for the cosecant, oh my god, I haven't seen that in forever. Again, 3 flavors. I think I'm going to go with the middle one. 2 divided by this, except that it's subtraction. All right, let's double check these fellows. Let's also see what chat thinks about all of this. Shelving would be determined by user. So not a computational value, perhaps, meaning user defined. Yeah, so the fact that you're using shelving instead of some other type is determined by user. But I'm not really sure what you mean by all this. Yeah, what kind of filter that you're using is determined by the user. But some of the other things like the big A and onwards up to the B's here, all of these lines are not determined by the user. They are computed from these other parameters like the filter type, the frequency cutoff, or the cutoff frequency, and the wideness, the Q or the bandwidth, and the B gain in case of shelving. Does that answer the question? Not sure I understand the question, but maybe it does answer the question. I don't know. So coming back to the Wikipedia article, let's just double check that we copied the formulas correctly. Yeah, that one seems right. That one checks out. Tangent, we are using this formula. No, that one. Cotangent. And then this one, we are using this formula. And then for this one, we are using this formula. All right, everything I think checks out. So I'll leave here to do tests for these. Just say tests. And then over here, in this definition here, we can just use that because it has been defined. So with that, I think we've finished some of these definitions, but time's up, you all. Let's just do beta, right? Because if we do beta, then we have concluded this part, and then there is still the coefficients to do. All right, so beta, where is beta used? Oh, and I think I have to check something, right? I have to check that. Yeah, I have to check the situation of this big A. What is that about? Why do I have 2 lines here? I think I made a mistake, didn't I? This big A should not be there. Yeah, I don't think it should be there. So we are computing the alpha. And to compute the alpha, we only compute the alpha under this condition. And then the Q and the bandwidth need to be set appropriately. So I think I need to do some error checking over here. I think I'm missing some error checking to do. Probably missing error checking related to, what is it? Alpha. And beta. I'm sure that beta will have a similar story. And then, yeah, for beta, let's do this. All right, for shelving EQs only. And then we use the slope if necessary. So we have an equation for Q, we have an equation for slope, and we have an equation for bandwidth. Oh no, these two are equivalent. This is equivalent to that. And I think that this has fewer operations, so I'm probably going to use this last one. Okay, so for beta, we have to check if I have a type of Q. Well, first of all, I have to check if I'm going to need beta, and I think that beta is only used for shelving. So I have to check if I am in a shelving situation. So if my shelving is, so if my type is different from low shelf and high shelf, I am in a non-shelving situation, then beta is undefined. Otherwise, I have to use this notion again of Q. So if I have defined stuff with Q, and I don't have an equation for bandwidth in this context, so I'll have to do some error checking for that as well. So if I have a Q, then this is the formula, square root of alpha divided by Q. And this A is not A. I think I'm going to need a big A situation here, and I need to find where I'm computing the big A, which is right there. And then I need to have a big A sort of situation there. Because I will need to use this down here. So this is not capital A, it's big A, and this is not Q, it is that. No, it is this. And if I am not on the bandwidth type, but on the S type, then I can use this formula. And these are, there shouldn't be square brackets, they should be parentheses, and this should not be capital A, it should be big A, and this should not be S, it should be the wideness value. And I'm going to put some spaces around this, and then remove that space there. Yeah, that's how I like to style my formulas. And power 2 is not the best way in terms of performance, but I also don't think it describes the equation so well, so I'm going to use SQR, which is probably faster. And I think it represents the intent just as well. And there you have it. We computed beta. Now, of course, I don't have the time to actually test all of this, but if it just compiles, then I'm happy. Just gonna call it a day if it compiles. It compiles. So there you go. Probably doesn't work. So let's see. We have these new hyperbolic functions, missing tests. We moved some stuff around. And then we renamed, or we fixed the way that the structs are being used. Then we created this whole shenanigans that is just a sketch, a rough sketch of what we will end up doing. So the schedule is that tomorrow I will be recording some music here on this channel, and then on Thursday I will be back to finish off this Rbj filter situation. I will answer any final questions and check out. Bob says, I was talking about why there were no parameters for computing shelving. Well, there are different parameters. But maybe you mean this formula? Maybe. I think that there is a formula. As I said, maybe I'll put a to-do here when computing beta, which is this part. So fix me. Allow for shelves with bandwidth? Question mark, because there is a formula. I'm not sure if it's in this document. I'll read this over again. I'm not sure it's here, but I know there is a formula to relate queue and bandwidth, but then even the definition of queue is kind of debatable, so I'm not sure if this should be done, hence the question mark stuff. Yeah, I don't know. Time for me to order a book. Thanks for the videos. All right. 10 and 10 hyperbolic is not the same thing. No, one is the tangent and the other is the hyperbolic tangent. For more on that, I am going to read this Wikipedia article, and if it makes sense, I'll tell you all about it. And I think that's all the time we have today. I see you again tomorrow. We'll be recording some stuff. It will be a lot of fun. Thanks for being here, for supporting me in all the different ways that you do, and I hope you're liking this. I'm going to push all of this to GitHub. Let me just do this now so I can actually wrap up the episode. So if you're interested in this, there is a link below to find my GitHub repository where I have all my JSFX stuff. Everything is published on Repack except for this library because it's a work in progress. So every day, by the end of the day, I have to delete these two files, come over to these files, drop them there, commit them here, and push. And now you'll be able to see this using the link below. That's all for today. I see you again tomorrow. Bye. Oh no, my keyboard shortcut didn't work. See, I'm saying bye, but I'm not going away. How about this? Bye.